Hello and welcome back to the second chapter of the Energy Systems Engineering module. As you look at this summary slide again, you'll see Chapter 1 consisted of our introduction, including green buildings, LEED, Energy Star. We looked at some important math concepts and utility bills and finished Chapter 1 with energy accounting and procurement. And now we begin Chapter 2, lighting. If you're involved in energy conservation, you know by now that improving the efficiency of lighting is typically or often a first pass for reducing energy consumption. And the reason is that lighting as a proportion of expense can be substantial. Another reason is that the lighting retrofits available can offer substantial improvement. You can see from this chart, nearly half of retail expense is lighting. One additional piece of context, however, for lighting expense, let's look, for example, at an office building. Although lighting expense was over 25% for an office building, as a proportion of expenses, think about the expenses incurred by the tenants of those office buildings, the rent, and the salaries of the people in those buildings. So make sure that as you consider lighting retrofit, which is 52 cents a square foot in this example, that you don't negatively impact the productivity of the people in that space. And you don't negatively impact the ability to rent that space. We're going to begin the lighting energy engineering system discussion with some definitions, but first let's take a little detour. You may recognize this as a first-generation electric lamp. However, indeed, it was Humphrey Davy, 70 years before Edison, who actually invented and patented the electrically powered light. Edison is most known for making it commercially viable, making it commercially producible. So just like Eli Whitney didn't invent cotton processing, we here in the United States typically benchmark his invention as a foundational turning, a foundational place in time where cotton processing was changed. Edison's commercial viability, commercial producibility was that turning point in lighting. But maybe enough general education. Let's move on to the definitions, followed by a section on lighting technology, and last in the technology section is occupancy and dimming. Although most of you won't be involved in lighting design, there are a few terms that, although may appear to be duplicate, these are design-specific terms that a lighting designer will use to explain why they do the things that they do, why they make the choices that they make. And so I thought just a minute of introducing these lighting design terms might help you, again, in the context. When the conversation turns to lighting, you'll have a better understanding. The first is illuminance level. It's lux or foot candles, and this is how much light a luminaire emits and is perceived at a surface. Not how bright the luminaire itself is. Brightness is more about distribution. Luminance ratio, this has more to do with brightness and is defined as the ratio of illuminance into areas. So if the illuminance ratio is 1, the ratio of the illuminance of the two areas is the same. If the ratio is either 0.5 or 2.0, one of the areas has double the illuminance of the other. Glare is the creation of bright and dark spots in the eye and causes eye strain. Have you ever noticed that it might be tough driving during the day? You might be uncomfortable. But it's nearly impossible to drive to keep your eyes open when there's one spot of high reflection, high illuminance from, say, a mirror in the trunk on the truck in front of you. That's glare. Uniformity is expressed as uniformity ratio, which is the average foot candles, the average illuminance, divided by the minimum foot candles, minimum illuminance. An example would be why you can see in moonlight. While the foot candles, the illuminance is low, the uniformity is very high. And the difference between horizontal and vertical surfaces. Understanding the illuminance of horizontal versus vertical, would the lighting design be different for, say, an architect lighting a counter, or for an interior designer lighting a vertical surface such as retail clothing? The last term here in lighting design is the inverse square law, and what that says is the illuminance reduces as the square of the distance. So if the distance doubles, the illuminance goes down by a factor of 4. Some of these terms may be new to you, but for everyone it's important that you know these terms in order to be engaged in that conversation that we keep referring to, that hypothetical conversation when it turns to lighting. The first term is watts. You all know what watts are. You see it on a light bulb, a 60-watt bulb, a 100-watt bulb. But the definition of a watt, it is a unit of power. 1 watt is the power produced by 1 amp across a potential of 1 volt. So watts indeed are a measure of power. Lumens are the perceived power, the power of light emitted in all directions. You see lumens rating on a lamp along with the watt rating. In contrast, the foot candles would be the illuminance we discussed in design, which is the amount of light that actually falls upon or is perceived by a surface. Let's press the pause button here and say that watts and foot candles are very important to us, and the reason is efficiency will continue to be presented in watts, in lumens per watt. How much light can you make per watt? In contrast, foot candles will be the measure of the effectiveness versus the efficiency. The effectiveness. How effective is your lighting system at delivering light to the surface where you need it? The next term, kilowatt hours, is again probably very familiar to you. It is a measure of work. A measure of work. 1 kilowatt hour is the work done by 1,000 watts of power over a period of 1 hour. And next is color rendering index, the CRI. Color rendering index typically is between 0 and 100, although you'll see an exception later. And it's the measure of a light source's ability to distinguish colors. The color temperature, or coordinated color temperature, CCT, strictly speaking, it is not indexed to or related to in that way the CRI. You can see from this graphic that color temperature is indeed exactly what you think it is. It is the temperature of the lamp's light. Consider a clay pot. As you heat that clay pot, it might glow red. As you continue to heat it, it'll glow orange, then yellow, then white, because the temperature of the surface is going up. So you'll see that color temperature shift from black to red to yellow to white and eventually to blue. Ballast factor is specific to a ballast and lamp combination. It represents the percentage of rated lumens that's produced. The ballast efficiency factor, however, is a different ratio. It's the ballast factor divided by ballast input voltage. Be familiar with these terms, because as we said, we want you to be able to be engaged in the conversation when the conversation turns to lighting. The last two terms, the ballast factor and ballast efficiency factor, will be especially important as you begin to study and understand the working together of a lamp efficiency and ballast efficiency. The purpose of this one slide is to draw attention to the one environment where lighting retrofits occur more often than others and at a greater square footage and more fixtures and more lamps and more usage, and that's in office spaces. And because of the unique color characteristics of most offices, that is, bland, whitish, beige, the lighting quality, the lighting color temperature can be seen dramatically. Take, for example, daylight, which outdoors is a very natural color, but in an office may appear very blue, versus warm white on the right appears very orange, and on the surfaces typically in an office, cool white may indeed appear the most like natural light. In this example, as we discussed just briefly lighting design, I wanted to give an example of a lighting designer anticipating and solving a problem before it starts. And that is the problem of glare and shadows in an office environment. Shadows are mitigated largely by having a lot of fixtures so that the light comes at your desk in many angles. Or where you can't get light, such as an under cabinet, you put in a small under cabinet light. However, glare is difficult because of the computers present in most office spaces. So what this designer has done is use a reflected up light that is bounced back off of the white ceiling and diffused into the room. Just one example of an intelligent lighting design. You may wonder, well, what's the right light? And with that usage there, now is as good a time as any to confess that before I became a certified energy manager, I was a chemical engineer, not a lighting guy. And so to the people who are in lighting, I must apologize for my indiscriminate and improper use of the term light. Indeed, I know that the component of a lighting system that generates light is not called a light, it's called a lamp. But indeed, I call it a light mistakenly. Please forgive me. Going forward, two of the most important performance characteristics of a lamp are efficacy and lamp life. Efficacy, its units are lumens per watt. How efficient is a lamp at producing lumens of light per watt input? The other is the lamp life. How long will it last in thousands of hours? You want a lamp that has a very high lumens per watt and a very high lamp life. So what you can't see on this is what the perfect light is, because we don't include on here color rendering index or color temperature or how easy or difficult it is to change these. But for these two variables, what you can see is incandescent, tungsten halogen, those two mini heat generators are inefficient and short-lived, both because of the generation of heat instead of light. If you were a lighting designer, you would have to understand the technical ways light is produced, the differences in these ways light is produced. And again, although you're not, we will take just a few moments here in order to round your training and lighting out as a certified energy engineer, we'll take a few moments to present the technology of these different illumination sources. First is incandescent. It's type A, or what you might say is a regular light bulb. And incandescent also includes halogen. The term itself, incandescent, literally means glowing with intense heat. Included in fluorescent illumination sources are all shapes and whether the ballast is built-in or hardwired. HID, or high intensity discharge, includes, as well as others, mercury vapor, metal halide, and high pressure sodium. And lastly, we'll look at low pressure sodium and daylighting. Daylighting will be discussed in two different contexts. One, daylight harvesting, the daylighting illumination. Just like any of these other sources that create light, the technology of daylighting brings more natural light into the space, daylight harvesting. Contrast that to daylighting controls systems. In that regard, a daylighting control system is a sensor that detects the amount of natural daylight and adjusts the light output, the light that you created, adjusts that output so that you're not creating more light than you need. Although there are differences in how the different illumination sources create light, there is a similarity, and that is that the light is created through a process shown here by the steps 1, 2, and 3. Step 1 is some particle impacts an electron that's orbiting the nucleus of this atom, impacts that electron, imparts energy into it, and pushes that electron out to number 2, a higher electronic orbital, a higher energy level. Well, the electron is not comfortable there. It doesn't want to be there. So the electron relaxes back down to the orbit it was in. And when it does that, it releases energy in the form of a light photon. An interesting note is that different atoms, this nucleus could be a mercury atom, but different atoms have different electronic levels. So these electrons jumping back and forth between levels can produce light of different colors, different wavelengths, all the way from invisible ultraviolet through all the visible wavelengths and into invisible infrared. Incandescent lamps, being our first example of an illumination source, produce light also by the excitement and relaxation of electrons. In incandescent lamps, the electrons are excited through the creation of heat, which is created by passing electricity through a filament of high resistivity and making it glow. The tungsten halogen lamp on the right is a type of incandescent light, or lamp, but it achieves a better energy efficiency than standard type A lamps on the left. The reason is that the tungsten halogen, the name tells you tungsten, which happens to be the composition of the filament. Halogen is an inert gas that is inside the lamp. In addition, there's a coating inside that glass enclosure that keeps the heat in. So the halogen gas and the coating on the glass enclosure keep that heat in and cause that tungsten filament to require less electricity to stay hot and glow, therefore more electrical efficiency. Indeed, tungsten halogen can be much more expensive to buy than a standard incandescent lamp. But because of this built-in efficiency, it's much less expensive to operate. The purpose of this graphic is just to illustrate the diversity of lamp geometry. Lamp sizes in the U.S. are on the dimensions of 1/8 of an inch. And what we mean by that is, take for example a F as in Frank 15. An F15 would be an F shape. That's the top row, fourth from the left, flame. And the 15 would say that its diameter is 15/8 of an inch, 1 7/8 inches. A T12 would be a tubular lamp that is 12 1/8 of an inch in diameter. And as you look through this list, you'll see the type A, top row middle, as the regular lamp. You'll see R for reflector. You'll see PAR for parabolic. And you'll see some other geometries that you in your operation or in your customer site are used to seeing. Compact fluorescents here in the United States are becoming much more accepted as a lamp replacement. Around the world, they've been accepted for a long time, and the reason is it's a simple unscrew the old and screw in the new. It requires no retrofit. And you see here compact fluorescent lamps that have a variety of different geometries. One example would be the globe geometry in the lower left. This is meant to replace a globe lamp, a globe incandescent lamp that's visible outside the fixture. Of course, if you put a spiral lamp, the one above it, in that fixture, it wouldn't look right. Fluorescent lamps work. Remember our conversation about how all lamps create light. Fluorescent lamps work by ionizing a gas, which then excites electrons in a mercury atom. The complexity here is that in a fluorescent lamp, when that electron relaxes and emits a photon of light, that photon is in the ultraviolet wavelength. It's not useful for creating light. However, you notice fluorescent lamps have a white coating on the inside. That phosphor coating inside the tube, when its electrons excite up from the impact of the ultraviolet light, when those electrons in the phosphor relax, they produce visible light. And depending on the phosphor coating, you can get different colors of fluorescent light. The compact fluorescent lamps here in the lower right are just to provide another picture showing how a pin lamp and this letter F can be used in a retrofit, as well as a circular lamp being used in a retrofit. As we looked from the very beginning at the overwhelming benefit and acceptance from relamping as an energy conservation effort, because you have that context, I want to present 3 of the most common relamp or lighting retrofit technologies being used: T5, T5 high output, and T8. We'll compare T5 and T8 in another way a little later. For now, what you can see is clearly T5 high output has a higher output, nearly double. But again, nearly double the lamp watts. So that the lumens per watt, plus or minus 10% on all 3. Lumen maintenance, plus or minus a couple percent. And rated hours, essentially a wash. And we'll look later at why you might choose a T5, a T8, and so forth. But these are the 3 most commonly used lamp retrofits or lighting retrofits. We're going to include cold cathode in this conversation because you will see these if you're going to be looking at your customers' properties or at your own operations. You will see this technology. For cold cathode, you can think basically of a neon fixture, although this is likely oversimplified. Think of a neon tube. Some of the benefits are it's flexible. Look at this picture. The non-linearity is a benefit of a cold cathode lamp. In addition, the continuity. You don't see gaps here because as you butt the fixtures, the lamps end to end, that gap is small enough that you can't see it. You can have many different colors. These can be dimmable, and they're very long lasting, which is fortunate because they are quite expensive. There is a componentry, a side of fluorescent lighting that we haven't discussed here as we walk through different types of fluorescent lighting, and that is the requirement of a ballast in fluorescent lighting. Think of a ballast on a ship. A ballast on a ship is meant to keep it at a certain depth. A ballast on a fluorescent lamp is meant to keep the current at a certain level. And why is that? Why is that necessary? Well, in most materials, conductivity at a given temperature is constant. In a gas, however, conductivity increases as current increases. Therefore, if left unchecked, the current could cascade to a point where lamp failure would occur. The ballast allows for the conductivity in the gas, such as gas found in a fluorescent tube, to be controlled. There are two ballast types pictured here. They look very similar from the outside. The first is a magnetic ballast. It works like an inductor, controlling current in a fluorescent light and running at approximately 60 hertz. This low frequency can cause a visible flicker and even make a humming noise. An electronic ballast, on the other hand, utilizes semiconductor circuitry and operates at a much higher 25,000 to 40,000 hertz. This produces no flicker, no noise, and can be 40% or more efficient. What about this silver cylinder here? A starter. Well, there's good news for you. Unless your fixtures are 10, 15 years old, there's a good chance you don't have a starter. The purpose of this 20-second detour and this picture is to illustrate for those people caught off guard by the use of the term hertz or cycles and the magnitude of the difference between electronic and magnetic ballasts. These 5 cycles, 5 peak to peak or valley to valley, 5 cycles in a magnetic ballast would take about 1/10 of a second, 0.083 seconds. In an electronic ballast, these 5 cycles would take about 1.5 ten-thousandths of a second. Earlier, we presented T5, T5HO, and T8 as the most popular lamp and relamp opportunities being used today. And we said we would look later at some of the benefits that weren't on that sheet of lumens per watt and rated life. And one of them is which one should be used given your operation or your customer's operation as it pertains to ambient temperature. Indeed, T12 fluorescent lamps have fallen on disfavor and are a great candidate for T8 or T5 replacement. And some would say T5 are always better, but what about temperature? What this graph shows is if you're operating at 30 to 50 degrees, T5 is almost always better. But what about if you're relamping a cold storage facility? Is T5 always better? Well, this manufacturer's T5 and most manufacturers' T5s at cold temperature are not as efficient as a T8. So consider just a graphic reminder to consider the context of your specific relamping project as it pertains to temperature. The HID is an example of a gas discharge lamp that works by passing an electrical arc, a little tiny lightning bolt, through a mixture of gases. This mercury vapor lamp, mercury vapor is going out of favor because of the mercury in it, but keeping in context the overwhelming replacement of incandescent with fluorescent, which also contains mercury, and one wonders how far out of favor mercury vapor will end up going. But walk through the components of this line drawing, and you'll see the components are there just like fluorescent, with a purpose of managing voltage and current flow during starting an operation. And whether mercury vapor or high pressure sodium, you see the arc tube in the middle and a relatively similar geometry. There is one type of HID that begs a little more description, and that's a metal halide. Metal halide lamps are similar in construction and appearance to mercury vapor or high pressure sodium, but the addition of metal halide gases to just mercury gas within the lamp results in higher light output, more lumens per watt, and even better color rendition than just mercury gas. The distinction, however, comes in where the configuration can either be a probe start or a pulse start. Traditionally, metal halide lamps used a probe start technology. In this, there are 3 electrodes present in the arc tube, a starting probe electrode, and 2 operating electrodes. To start the lamp, a discharge is created across a small gap between the starting probe electrode, also known as a starter electrode, and the operating electrode. Electrons then jump across the arc tube, that miniature lightning bolt, to the other operating electrode, and that helps start the lamp. Once the lamp is started, a bimetal switch removes the starting probe electrode from the circuit. In contrast, a pulse start metal halide lamp does not have a starting probe electrode. Instead, there's a high voltage igniter that works with the ballast to start the lamp using a series of high voltage pulses, typically 3,000 to 5,000 volts. Without the probe electrode, the amount of pinch or seal area at the end of the arc tube is reduced, and that results in reduced heat loss. Furthermore, using an igniter with the lamp reduces tungsten sputtering. This is the deposition, the evaporation of tungsten from the filament to the inside of the glass. Warm-up time can also be reduced. With those benefits, you can see that the pulse start technology was developed to increase lamp life and energy efficacy of the conventional or the historical probe start. Low pressure sodium is another gas discharge lamp. Its geometry may be a little different. These dimples, these sodium retaining reservoirs are a little different. But you see a similarity to a tungsten halogen lamp in the glass coating inside. Glass coating is used to reflect the heat in the lamp, to keep the heat in. Heat being a process that increases lumens per watt. But low pressure sodium has a drawback. Its color. We'll see a little more on the color on the next slide. But what you see here is, if you recall, low pressure sodium had a very high efficacy and very high lamp life. But it's yellow. And so the use of low pressure sodium, you may see it a lot on public lighting, highway lighting, parking lot lighting, where you need lighting for safety, but the color of the light is not as important. Here's the spectra. Here's the proof in the handicap of low pressure sodium lighting. The lighting spectra of low pressure sodium, high pressure sodium, and mercury vapor illustrates the monochromatic light from low pressure sodium. It is a dark yellow. It also illustrates that high pressure sodium has a broader base of color, but still centered around yellow. Mercury vapor, however, you see has strong color bands across the visible spectrum, from violet to red. Something that we did frequently during the authoring of this Certified Energy Engineer course was decide what gets in and what gets out. One of the things we wanted to introduce in terminology, but allow you to take your own time if you're interested in the definitions, is the introduction of HID ballasts. The reason we bring these in is because oftentimes the HID lighting is referred to by its ballastry. So take, for example, reactor ballasts, normal power factor and high power factor. Then consider auto transformer ballast and the three types listed here: auto lag low power, high power, and constant wattage. And the last two, constant wattage isolated and mag-reg. Just know these terms, because if you hear these terms, then you know the lighting they're talking about is HID. I must apologize to those of you with a weak stomach, but when I was looking for a picture, a good representation of a semiconductor, I found this picture of a half of a conductor, a semiconductor, and I just couldn't resist. But indeed, a semiconductor pictured here is more relative to our discussion, of course. In our discussion, a diode, we're going to be talking about light-emitting diodes. A diode is the simplest form of a semiconductor. A semiconductor is neither electrically conductive nor insulative. It's something that isn't typically conductive, but can be doped into or tricked into being a conductor. LEDs use electricity and semiconductors to generate photons of light. There's an interesting back and forth here. Look here, you can put electricity across a semiconductor and generate light. You'll see in solar power you can put light into a semiconductor and generate electricity. You'll see these back and forth as well with motors and controls and wind turbines, for example. But that's another time. Although LEDs you see here don't have a filament that heats up and wastes energy like an incandescent lamp, the whole LED efficiency is largely tied to ambient temperature. Therefore, when you see LED solutions, you'll see them as fixture and lamp combinations designed together, because the integrated heat sink, that part of the fixture that gets rid of the excess heat to keep the LED efficient, that integrated heat sink must be designed for that LED fixture. For every other light source, we try to present a picture of the flow of electricity and the generation of light. This is an LED, a light-emitting diode. Its construction has terminal pins, those things that bring in and take out the current. There's a diode that when there's a current across there, it generates light. That light, the wavelength of that light, is a function of the diode. LEDs can be present in different colors. We'll talk on the next slide about white LED and why it is more difficult, and two different ways of creating white LEDs. But what you see on this graph is that the diode that you use, when you put a voltage across it, will either create blue or green or red, a specific wavelength of light, or it can make a broad wavelength of lights, plural, that look white. There can be white LEDs that are indeed like a miniature fluorescent. The diode actually creates UV light. The LED actually has phosphor coating, so that UV light excites the phosphor just like in a fluorescent light. You can also have non-phosphor LEDs, non-phosphor white LEDs, and what they do is they generate a combination of colors. If you look at the picture on the left, if you combine color pigments, you get black. Combine cyan, magenta, and yellow, you get black. This is what happens on your inkjet printer if you run out of black ink. You can create it with those three colors. In contrast, if you combine light, wavelengths of light, blue, green, and red, three primary light colors, you'll get white. And a non-phosphor white LED is just that. Create the right combination of colors that create a white light. We're going to begin looking at some LED examples. Because LED is a more recent technology, it's not new, but it is a more recent technology, some may think that it's experimental. Well, here are some examples, some proper usages of LEDs. Look at this freezer cabinet on the left. You can see the LED light strip going up in the mullion between the doors. Indeed, there are even motion sensors, the small black boxes, above the doors, so that these LEDs are off when there's nobody in the freezer section. And of course, one of the ways you can measure whether a technology is widely accepted is whether there is a rebate available to install it. And in California, there are several rebates available for people installing LED, particularly in refrigerated and in freezer cabinets. Although most people taking this course are not residentially inclined, here's a great example of using LED technology for a very quick payback. This landscape lighting uses 36 watts with the LED system versus 600 watts of 12 volt power on the previous system. 36 versus 600. This last example of LED is for retail. Note, we don't define things in and of themselves always as good or bad. Take, for example, glare. We typically think of glare having a bad connotation to it. But we define glare simply as the difference in light. And here, retailers use glare to their advantage. In this case, using LED lights, which can have an opportunity or a negative impact because of glare. In this case, that small, powerful, bright light of an LED is being used to highlight and draw attention to merchandise. This next illumination source, induction lighting, has benefits of long life, good color, but high cost. Induction lighting can last 100,000 hours and have great color. So one rule of thumb is, if the lamp or the fixture is hard to get to, put in induction, because you won't have to replace it for a long, long time. Nearing the end of this chapter, let's take a minute together to look through this lighting technology, illumination sources that we've looked at so far. And you won't need to press pause. Stay with me. I'll give you a minute to answer these questions, or a few seconds to answer these questions. I want to know, as you look at this graph, the strength or a strength and the weakness or a weakness of each of these four lighting types. Again, what's a strength and what's a weakness? Starting with incandescent. A strength of incandescent could be its color temperature. It is a nice color. Its color rendering, in addition, its ability to allow you to distinguish colors is very good. Now, what is one weakness? Pick one weakness. Well, as you can see from this table, and as you saw on a previous slide, incandescent bulbs are weak in efficacy and lifetime. And now do this exercise, a strength and a weakness, with fluorescent. A strength would be its long life and high efficacy. Weakness, color. What about high intensity discharge? Strength and weakness. Again, strength, like fluorescent, can be long life and high efficacy. Weakness, although you can have strong color temperature, its color rendering is not as good. And low pressure sodium, efficacy and lifetime, you see here, you saw it on the previous chart, is good. Color rendering index, look, we're not even between 0 and 100 anymore. Why is that? Because the color, the weakness of low pressure sodium is its monochromatic yellow. The last illumination source we'll consider is daylighting. In many cases, there is sufficient natural light outside. If we could only get it inside and distribute it better. Skylights are the most common form of daylighting. You won't find a Walmart or any other big box store built in the last 5 years that doesn't have a significant presence of skylights. Tubular skylights have been used in the past as a residential application, bringing natural light into a dark hallway or focused light into a laundry room. But more and more, tubular skylights are being accepted in industry to bring a focused beam of light to a work surface. The third daylighting is pictured here in a light shelf. A light shelf is a configuration that allows daylight to come in through the bottom of the window, but the daylight through the top is reflected up onto the white ceiling and diffused further into the room. Here's another picture of a daylight harvesting fixture with a red tubular awning shade fixture on the outside. And on the inside, that white shelf is designed to reflect light that comes in through the top half of this window off that high reflectivity shelf and up onto the ceiling, bringing daylight further into the room. Next is our section on occupancy and dimming. With respect to natural light, you can have photosensors and daylight dimming. Remember earlier when I differentiated daylight harvesting as an illumination source and daylighting as a control system. Well, this is daylighting as a control system. As it pertains to natural light, you can have a photosensor that determines how much natural light is coming in. That sensor feeds back to the control system and dims the light you're producing so that between the light you produce and the light coming from outside, you have an appropriate level of light. One of the concerns and one of the things to be aware of is make sure your control system is chosen well, because otherwise you can have a control system that's fighting itself. Natural light is going up, created light is going down, and those two battle themselves, and you can see this result in a flicker or a visible change in that lighting. In occupancy, you can have sensors that are simple, like a passive infrared in this ceiling mount example in the lower left. Or, like the picture on the right, you can have multiple technologies that are combined that detect heat, motion, sound. Clearly, the more technologies you can use to make sure nobody's in the room when you turn the lights off, the fewer complaints you'll have that somebody turned the lights off on you. Note that either of these sensor types can be present in what's called bi-level switching. And indeed, some tax codes require the presence of bi-level switching so that the switch is not turned off but turned down. With any of these, make sure that you match the customer needs. Remember the dramatic difference between the cost of lighting and the cost of the salaries of the people or the rent of the space where you're doing the lighting. And make sure that your occupancy and dimming strategies don't negatively impact those people. As we've come to the end of Chapter 2, let's do a quick review on lighting. First is we went through some definitions that you have to be familiar with so that you can be involved in the discussion when it turns to lighting. Next is we discussed the lighting technology in two forms: illumination sources, the technology available for illumination, as well as some technologies available for occupancy and dimming. And not in this order, but last on this list, we also discussed some lighting design concepts. Again, these concepts are presented not because you're going to be a lighting designer if you're not now, but because if you're going to be involved in the conversation with your lighting designer, you need to know illuminance level, luminance ratio, glare, uniformity, why is horizontal versus vertical surface is different, and why when you double the distance do you bring the light at a surface down by a factor of 4. Let's go on to Chapter 3.